Hello dear students, now we will discuss motion of a charged particle in a uniform magnetic field. Here there are three things. One is, what if the charged particle is moving parallel to the magnetic field or anti-parallel to the magnetic field? Second case is, what if the velocity of the charged particle is perpendicular to the magnetic field? Third case is, what if the angle is not 0, not 180 and not 90 degree? Then what happens? Okay, there are three cases. Okay, we will discuss the first one. Okay, if velocity of the charged particle makes an angle 0 degree or 180 degree with the direction of magnetic field. Okay, now say here I consider some uniform magnetic field. Okay, there is some charged particle here, plus q is the charged particle. It is moving in the direction of magnetic field. It is moving with the velocity in the direction of magnetic field. Now what is the magnetic force? We know magnetic force is equal to QVB sin theta. Magnetic force is equal to QVB sin theta. So what is theta here? Theta is the angle between velocity and magnetic field. So here in this case, angle between velocity and magnetic field is 0 degree. Okay, so sin 0 is 0. So the magnetic force is 0. Means that positive charge will not experience any force when it is moving parallel to the magnetic field. It moves as if there is nothing. Okay, next, if the charged particle is moving with a velocity which is anti-parallel to the magnetic field, say the same charged particle plus q, if it is moving with velocity opposite to the direction of magnetic field, then also magnetic force will be equal to 0, because we have sin theta. In the place of sin theta you substitute 180. Sin 180 is also 0. So therefore magnetic force is 0. Okay. Now the second case, what if the charged particle is moving such that its velocity is perpendicular to the magnetic field? Now what I'll do, I'll consider a uniform magnetic field like this. Okay, so this is uniform magnetic field. If I put into symbol, okay, into symbol means what? Magnetic field is going into the plane of the paper. Magnetic field is going into, that is why we put into symbol. So here I have considered a uniform magnetic field. Okay, now let us suppose that there is a positive charge here, plus q, which is moving in a direction perpendicular to the magnetic field. Now if I have put into symbol means what? Okay, magnetic field is into the plane of the board or into the plane of the paper. Okay, velocity is in this direction. What is the angle between magnetic field and velocity? 90 degree. Okay, now what happens? To know the force acting on the charged particle, we have to use Fleming's left hand rule. Okay, in case of Fleming's left hand rule, if the forefinger gives the direction of magnetic field, it is into the plane of the board. Okay, if the central finger gives the direction of motion of positive charge, or if it gives the direction of current, okay, then thumb gives the direction of force acting on the charge. So this is the direction of force. Okay, so because of that force, what happens? The charged particle will start moving like this. Okay, when it comes here, what is the direction of velocity? This is the direction of velocity. Again you apply Fleming's left hand rule. Magnetic field, forefinger should give the direction of magnetic field. It is into the plane of the board. Central finger should give the direction of motion of positive charge. We have considered positive charge. Now the thumb is giving direction of force. So this is the direction of force. Okay, so you observe here, force is pointing towards a particular point. So again this progressively the charged particle moves like this. When it comes here, see, this will be the direction of velocity. Okay, now magnetic field is into the plane of the board. Now central finger gives the direction of positive charge, so thumb will give the direction of force. Force is downwards. Okay, so due to this, again the charged particle will come here. Okay, charged particle comes like this. Here at this position, this is the direction of velocity. So forefinger points the direction of magnetic field. Magnetic field is into, charged particle is coming down, so this will be the direction of force. So what happens? The charged particle describes a circular path. If the velocity of the charged particle is such that it is perpendicular to the magnetic field, uniform magnetic field, then the charged particle will prescribe a circular path. Okay. Next, what is the third case? If, see the previous case here, we can calculate the equation for radius and time period. That I will do in the next video. Now here, third case, what if theta is not equal to 0 degree, theta is not equal to 180 degree, and theta is also not equal to 90 degree. Now what happens? Say I have considered a uniform magnetic field. This is uniform magnetic field. Okay. Now let us suppose that this is the uniform magnetic field. Now let us suppose that a charged particle plus q is fired with a velocity v, which is making an angle theta with the direction of magnetic field. Now what happens? See this velocity, okay, I'll write it here, okay, that velocity has two components. One component is in the direction of magnetic field, that is v cos theta, correct now? Okay, v cos theta is in the direction of magnetic field. V sin theta is perpendicular direction of magnetic field. Now you look at the first case. If the velocity is going in the direction of magnetic field, it will move along the horizontal. It will move straight. Correct now. Now if the velocity is perpendicular to the magnetic field, correct now, magnetic field is inside, velocity is in this direction, then it will move in a circular path. Then there will be a centripetal force acting. Correct now. That means vertical component of velocity will be responsible for circular motion, okay, and the horizontal velocity, if the velocity is in the direction of magnetic field, then it will be responsible for horizontal motion, okay. So therefore, here in this case, v cos theta will be responsible for the motion of the charged particle along the magnetic field. V sin theta will be responsible for the revolution. Now what is happening? V sin theta is trying to it is responsible for centripetal force, and it is because due to V sin theta, charged particle should go like this because it is vertical component. Due to V cos theta, charged particle should go along the direction of magnetic field. So as a result, the charged particle will move like this. Okay, the charged particle move in a helical path. Okay, the charged particle will move in a helical path. Okay. Now in this helical path, what is this? Distance traveled by the charged particle in a time equal to time period. We call this as pitch of the helix. Pitch of the helix. Okay. So what is the equation for pitch of the helix? Pitch of the helix, since pitch is distance traveled, correct na? Pitch is equal to, so who is responsible for horizontal distance traveled? V cos theta is responsible, correct na? So pitch is horizontal distance. Horizontal distance means horizontal component of velocity into time. So we know the equation for time period. Okay. So if you substitute the equation for time period, we will get the equation for pitch. Or generally pitch is equal to horizontal component of velocity into time period. So our pitch is equal to horizontal component of velocity is v cos theta into time period is 2 pi m by qb. Okay, 2 pi m by qb. This however we are going to derive in the next video. Thank you very much.